Welcome to Discrete Mathematics. Today we are going to explore a fascinating concept called lattice products. If you have ever had to make a decision based on multiple independent factors, like choosing a car based on both speed and safety, you already intuitively understand how this works. Let us dive in and see how mathematics handles these multi-dimensional choices. Before we look at the math, let us understand why this concept matters. Imagine you are buying a car. You care about two things: engine power and safety rating. Car A is only strictly better than car B if it has both a better engine and a better safety rating. But what if car A is faster while car B is safer? In that case, they are incomparable. Neither is universally better. A lattice product takes two separate ranking systems, like speed and safety, and glues them together into one combined system. This allows us to make rigorous decisions by looking at each trait completely independently. Now that we understand the intuition, let us define this mathematically so we can work with it. Suppose we have two separate lattices, which we will call L1 and L2. The lattice product is the collection of all possible ordered pairs, x, y. In these pairs, the first piece always comes from the first lattice, and the second piece always comes from the second lattice. To make this new collection of pairs into a working lattice, we need rules for comparing and combining them. We do this strictly component by component. This brings us to our first rule: how to combine two pairs to find their least upper bound, or join. Conceptually, this formula tells us that the join of two pairs is just a new pair made by joining the individual pieces side by side. The symbol V represents the join operation. The variables A1 and A2 are elements from the first lattice, while B1 and B2 are from the second lattice. By evaluating the join for the first components and the second components completely separately, we guarantee that the new pair is the smallest possible combination that is still greater than both original pairs. If either starting component increases, the resulting joint component will also increase or stay the same. Just like the join operation, we also need a way to find the greatest lower bound, or meet. The formula for the meet works on the exact same principle. The wedge symbol represents the meet operation. We calculate the meet of two pairs by finding the meet of the first components and the meet of the second components completely separately. This creates a new pair that represents the largest possible value that is still smaller than both of the original pairs. It is the exact mathematical equivalent of finding the shared foundation or overlap between two different multivariable states. If a variable in the starting pairs decreases, the resulting meet will also decrease or remain unchanged. Finally, we need a rule to determine if one pair is strictly less than or equal to another. This formula states that one pair is ranked lower than another pair if and only if its first part is lower in the first lattice and its second part is lower in the second lattice. The less than or equal to symbol represents our ranking system, and the double-sided arrow means if and only if, showing a strict two-way logical guarantee. If even one component fails this check, the entire pair cannot be considered less than the other, making them incomparable, just like a fast but unsafe car. Before we move on to any proofs, let us see this with a concrete example. We are given a simple chain lattice with two elements, 0 and 1, where 0 is less than 1. We want to find the elements of the product lattice C2 cross C2 and calculate the join and meet of the specific pairs 0, 1 and 1, 0. First, we list all possible ordered pairs by taking one element from the first chain and one from the second chain. Think of it like flipping two coins. This gives us four possible combinations, forming the complete universe of our new product lattice. Now that we have our universe of pairs, let us calculate the join of 0, 1 and 1, 0. We set up the join operation by looking at the first positions and the second positions independently. The first positions are 0 and 1, so we write them together with a join symbol. The second positions are 1 and 0, so we do the exact same for them. Since 1 is greater than 0 in our basic chain, the maximum of 0 and 1 is simply 1. Applying this to both components, the combined pair results in 1, 1. This is the lowest point that sits above both starting pairs. Next, we set up the meet operation to find the greatest lower bound for the same two pairs. We do this by again separating the first and second components into their own isolated calculations. We pair the first components with a meet symbol and the second components with a meet symbol. The minimum of 0 and 1 is always 0 in our simple chain. Therefore, the meet of these two pairs evaluates to 0, 0. This shows that while our two starting pairs cannot be directly compared to each other, they share a common floor at 0, 0. Let us visualize the math we just performed. You are looking at the Hasse diagram for our product lattice. At the very bottom, we have the shared floor at 0, 0. From there, you can move up along the solid lines to either 1, 0 on the left or 0, 1 on the right. Notice that there is no straight upward line connecting those two middle points because they are incomparable. To find a point greater than both, which is their join, you must continue upward along the lines to the peak at 1, 1. This perfectly illustrates how a one-dimensional line transforms into a two-dimensional diamond shape. Now, let us look at another example to see how the rules apply when the starting lattices are different sizes. We have a chain C3 with elements 0, 1 and 2 and a chain C2 with elements 0 and 1. We want to calculate the join and meet of the pairs 1, 0 and 0, 1. We use the exact same component-wise strategy. We pair the first components 1 and 0, which we will evaluate using the rules of the 3-element chain. We pair the second components 0 and 1, which we will evaluate using the 2-element chain. Let us evaluate the join we just set up. In the first lattice, the maximum of 1 and 0 is 1. In the second lattice, the maximum of 0 and 1 is 1. Putting these independent results back together, the resulting pair is 1, 1. This proves that the least upper bound is found by simply solving two smaller, easier problems and combining the answers. Next, we set up the meet operation to find the greatest lower bound by looking at the minimums of the respective components side by side. We are now ready to evaluate the meet operation for our unequal chains. The minimum of 1 and 0 in the first lattice is 0. The minimum of 0 and 1 in the second lattice is also 0. Combining these independent results, the final meet is 0, 0. This step-by-step process works flawlessly, no matter how large or complex the individual starting lattices happen to be. By keeping the dimensions separate, the math remains incredibly simple and structured. The physical meaning here is that 0, 0 is the highest possible state that is still a prerequisite for both of our starting pairs. Now that we have successfully used these formulas in multiple examples, let us prove why the component-wise join actually creates a valid least upper bound for the product lattice. We need to show that the combined pair is an upper bound for both of the original starting pairs. We will do this by looking at how the individual components behave in their own separate lattices. In the first lattice, the element A1 is naturally less than or equal to the join of A1 and A2. This is the fundamental definition of a join in any single lattice. We continue our proof by looking at the second component. Similarly, in the second lattice, the element B1 is strictly less than or equal to the join of B1 and B2. The second component follows the exact same logical rules as the first component, completely independently. We have now established that both individual pieces of our first pair are smaller than or equal to the pieces of our combined pair. This mathematical reasoning sets us up perfectly for the final conclusion of our proof, connecting the individual behaviors back to the product lattice rules. We will now combine these facts. This brings us to the final step of our derivation. Because both individual components are less than or equal to their respective joins, our rule for ordering pairs tells us that the first original pair is less than or equal to the combined pair. By applying the exact same logic to the second pair, we can easily see it is also less than or equal to this combined pair. Therefore, we have successfully proven that the component-wise join acts as a valid upper bound for both original pairs. This confirms our formula works perfectly and logically, giving us earned understanding. So we have proven that our lattice rules hold. This brings us to an important question. Why do we care about lattice products in the real world? In computer science and engineering, we rarely deal with systems that only have one variable. We usually have multiple independent properties to track at the exact same time. For example, in parallel computing, a system state might depend on the progress of several different processors. If processor A is at step 3 and processor B is at step 5, we can represent this state as the pair 3, 5. The lattice product gives us a rigorous mathematical framework to compare these complex states. We have covered a lot of ground today, so let us review the most important ideas. First, a lattice product is simply a way to combine two separate lattices into a single, unified system of ordered pairs. Second, by evaluating the meet and join operations strictly component by component, we maintain the structured ranking of the original sets without any confusion. Finally, this mathematical tool allows us to easily scale up simple logical comparisons into multi-dimensional spaces. You now have a complete understanding of how lattice products work, from the basic definitions all the way to their real-world applications.